Hello, welcome to Mystery Science. This video is for CP2, which is Forces, Lesson 3 or 4, depending on how you look at it, Mass and Weight. So you'll find it under most specs as CP2c. This is filmed for the Edexcel spec. Right, so today we're going to look at the difference between mass and weight. Why are they different? What is the difference? We're going to talk about the factors that determine the weight of an object, and then you're going to recall the formula for calculating weight because it's one that you have to remember, and you're going to get practice using those. Right, as a quick do now, if you've watched the previous lesson, then you should know this. If not, go back and watch that. These will all be packaged inside the same playlist, so you can watch them sequentially if you wish. Right, so the question is, what must be present for an object to move in a circle? Right, now you've come back to me. Obviously, if an object is moving in a circle, it is changing direction all of the time. If it's constantly changing direction, that means it's accelerating. If it's accelerating, there must be a resultant force, because Newton's first law says that the motion of an object does not change, i.e. doesn't change direction, doesn't change speed or velocity, unless there's an external force acting. So for an object to move in a circle, there must be an external force, and that is called the centripetal or centripetal force. Okay, so what is the difference between mass and weight? Well, the weird thing is, just like a few things in science, common parlance, the things that we say in everyday life, are out of context not correct. We'll often say, I'm going to weigh myself, and my weight is 100 and something kilograms today. Oh, I feel so heavy, my weight. And people will interchange the words weight and mass. Now, the mass is actually a measure of how much matter or particles an object has. I have 105 kilograms of awesome science teacher particles that make up this awesomeness. My weight, though, is dependent on how strong gravity pulls on all of my particles. So if I change my place in the universe, so for example, I was going to go to the moon, where the gravity is weaker because the moon is smaller than the Earth, what would change and what would stay the same? Pause the video, write down your answer. Welcome back. If you're going to travel to the moon, gravity is much weaker. Your mass will stay the same. You've still got the same number of particles. If I went to the moon, I'd still have 105 kilograms worth of awesome science teacher particles. They would not change. But my weight, however, would change because the force of gravity on the moon is much, much smaller. People often say to me, again, a common misconception, people will say, but there's no gravity on the moon. Yes, there is. There's gravity everywhere. Gravity acts between two objects. We'll look at that in a little bit. So this is something that you would have done were you in the classroom. So apologies that you can't do this, but you could try this out. But you need something to weigh the force. So you're using a force meter. So unless you've got one of those lying around, this is quite difficult. But what the experiment would normally be is you would have a bunch of objects and you would put them on a balance and it would tell you the mass in kilograms. Or if it was in grams, you divide that by 1,000. There are 1,000 grams in a kilogram. You'd then use a force meter or a Newton meter. You would then lift the object with the Newton meter and it would tell you the force. Now actually what's going on is inside the Newton meter is just a spring, and the spring has been calibrated so that for every kilogram it will move 10 newtons. That's it. I've kind of given away some parts for the rest of the lesson, so bear that in mind. So you then put this in a table. You do this for all the objects and you get a table that looks a little bit like this. So for every 0.1 of a kilogram, I have 1 Newton. if I had a mass of 0.3 kilograms, I should have a weight of 3 newtons. I've made this data up, but what I have done is I've added in a little bit of uncertainty to make it look like real data. Sneaky mystery. So you can see that actually all of these masses are 10 times smaller than the weight, give or take a little bit. That's interesting. So what would happen if you plotted that on a graph? So the next thing you would do is you would draw a graph. You'd have weight on the y-axis because that's the dependent variable, that's the thing that changes, and mass on the x-axis, that's the independent variable, the one that you change. You'd then draw a line of best fit, and you'd get a series of points which would form a straight line. And this would happen every single time. Now, if I was going to do this exact same experiment on the moon, I would still get a straight line, but it wouldn't be as steep. And if I did this on a larger planet, which was quite dense, let's say Jupiter, again, I would get a straight line, but it would be more steep. So what does this tell us about mass and weight? Well, if you look at the graph, you can describe the relationship between mass and weight. There's a straight line. If we have a straight line relationship in GCSE science, you need to know that that is called a proportional relationship. If it's a straight line going up, it is directly proportional. This means whatever you do to the mass, you will also do to the weight. If you double the mass, you will double the weight. So you can work out the weight of an object by multiplying the mass by a constant number. So the gradient of the graph gives you that constant. So you can work out the gradient of your graph. The difference in your weight divided by the difference in the mass, and that will give you the slope of that graph. Right, so if you do this experiment on Earth, which I hope you are doing, unless at some future time and you've all gone to the moon to do this experiment, you will find that the gradient of your slope is roughly 10. So the gravitational field strength on Earth has a value of about 10 newtons per kilogram. Every kilogram pulled down with a force of 10 newtons. If we went somewhere else in the solar system, this number would change. On the moon, it's about 1.6. So for every kilogram, the force would be 1.6 newtons. And the gradient of my graph, which would be less steep, as I've said, would give you a value of around 1.6. In fact, the gravitational field strength of the Earth is about 9.81. When you do A-level science, A-level physics, we use the exact value. Whereas for you guys, you just need to remember that it's 10, which is nice and simple. And it makes all the calculations really easy. Multiplying by 10 is simple. When you go to a different planet, though, it's a slightly different matter. Different matter. Amount of matter. Mass. Okay, it's just me. Right, so gravity. What is it? What is gravity? It changes on different planets. Why? Why does it change on different planets, Mr. E? What are you talking about? Well, gravity is a force. It's an attractive force that actually happens between any objects with mass. It acts on Earth by pulling objects towards the center of the Earth. But if we were floating around in space, let's say it's just me and my tea mug here. Now, if I was floating around here in space, the closest two objects would be myself and the mug. I would have a gravitational force on the mug would have a gravitational force on me. I am much larger than the mug, so this will float towards me. I will actually move towards it a tiny bit. And actually, the sun, actually on Earth, if you jump up in the air, the Earth will rise ever so slightly to meet you, but it's so imperceptible because the Earth is much more massive than you are. But this coffee cup would gravitate towards me. The force would pull it to me, and it would essentially stay on me. And so I'd be like the planet, and the mug would be like the person. But the ratio of the mass of this mug to the ratio of the mass of me is a lot different to you and the Earth. So this doesn't happen while we're on the planet. The mug at the moment is not gravitationally attracted to me with any kind of force that would be noticeable. I mean, it is attracted, but the force is so small in comparison to the force pulling everything down towards the center of the Earth. We just don't notice it. So the object with the heaviest mass has a stronger gravitational pull. It has a heavier weight. So the Earth is so much more massive than we are. We're all attracted to the center of the Earth, and that's why if there's a hole in the floor, you will fall down it. And if you had an imaginary hole that went through all the way through the center of the Earth, I get asked this every single time, and I bet this is no exception. You're probably wondering this. In theory, you would fall down through the hole to the center of the Earth, and you would accelerate all the way down, assuming there was no air, and then you would carry on moving through the center of the Earth, but you'd be slowing down now because you'd be being pulled back up. And so you would pop out a hole at the other side, be able to wave at some Australians or some New Zealanders, and then ping back that way again. That is a bland theory that actually wouldn't exist because you'd have a core drilled down through the Earth, and you'd be attracted to the center of the mass on either side. If you went dead center down the middle, that would work, but actually you'd be attracted to the sides and you'd just bounce down and get crushed to death by the pressure anyway. Anyway, the formula that you need to work out weight is this. Weight equals mass times gravity. W equals m times g. And that's not hard to remember because like all equations with just three things, you can use an equation triangle. I'm not going to show you the equation triangle because I don't like teaching them. But if you need to, you can work out how to do that. Okay. Apologies for that pause there. But if you are working out weight and you're on the Earth, the gravity will be replaced by the number 10. Wherever you are on the Earth, the gravitational attraction is 10. One of those lies I tell you at GCSE. But for your exams, all you need to know really is that number. And this is the weird thing about teaching at GCSE. I can teach you how to pass the exams, or I can teach you the actual science. For those of you interested, if you're not, skip a few seconds. But for those of you interested, actually the gravity changes no matter where you are on the planet. And this is because the planet isn't a sphere. It's kind of like an oblate shape, which is a bit like this. It's squashed at the top and bulges out of the middle. It's actually attracted towards the sun. You get what's called the tidal bulge. And because it's spinning, and so gravity is actually larger at the equator than it is on the poles. And again, the number isn't actually 10, it's 9.81. Join me for A-level physics for more explanation on this. Right, welcome back. Those of you that just want to pass exams and don't want to know the actual science, please learn science. It's really good. Okay, so we're going to solve some equations now. I'm going to teach you the Srow method. All of the kids in my class are now rolling their eyes and going, oh, not Srow again. But I will explain this for the benefit of everyone. Srow is a way to solve equations that genuinely gets you more marks in exams. If you do a calculation in your head in an exam and you write down the answer, if it's correct, you will get the full marks at GCSE. If, however, you get the wrong answer, you get 0 marks. If you have written down your working out using Srow, you will gain marks because they will know that you followed a process. They will give you marks for that process. You just will lose 1 mark for getting the answer wrong. So, what is Srow? E stands for equation. S, substitute in the values. R, rearrange your equation. Then work out the answer, and then don't forget at the end the units. Sometimes the answer without the units will get you 1 less mark than the answer itself. So all of these things are very, very important. Right, so this is an astronaut. His name is Sam. Hello, Sam. He can't hear us because there's no air in space, so sound can't travel. He has a mass of 90 kilograms here on Earth. Before I ask what his weight is, what's his mass in space? If he's 90 kilograms here on Earth, what is his mass floating around in space? Write down that answer. Hopefully, you have written down 90 kilograms because his mass doesn't change. No matter where he is in the universe, his mass is always 90 kilograms. But his weight here on Earth is the thing that's different. So here is Srow in action. We write the equation first, W equals mg. Then we substitute in all the numbers that we know. So in this case, weight equals 90 because that's his mass, 10 because that's the gravitational attraction on Earth. Little g is always 10. Do we need to rearrange it? No, because the subject of the equation is the unknown weight. So then we work out the answer. 90 times 10 is 900. Put the units on, its weight is a force, therefore it's 900 newtons. Okay, now the same astronaut, so he's still 90 kilograms, has gone to the moon. The moon has a gravitational attraction of 1.6 newtons per kilogram. What is his weight now? Srow! E, write down the equation. Always, very important. Sometimes you get a mark just for writing the correct equation. W equals mg. Weight equals mass times gravitational force. Now we substitute in the numbers. Weight is 90, that's still his mass, times 1.6. That is the gravity due to the force due to gravity. You will be given this for the planet that they're on. You need to know that the Earth is 10, so it won't give you 10 for the Earth. Do we need to rearrange? No, the subject is the unknown, in this case weight. So again, it's 90 times 1.6. The answer, 90 times 1.6 is 1.44, at least according to my calculator. And it's a force, so it's 144 newtons. Now then, Sam has a friend called Ed. They both go on a mission to the moon. Gravity is still 1.6 newtons. Ed has a weight of 100 newtons on the moon. What is his mass? So again, we use Srow. Now we use the full equation, weight equals mass times gravity. We substitute in the numbers that we know. The weight is 100 newtons now. 100. We don't know the mass, so 100 equals m times 1.6. That's the gravitational force. Now we rearrange because we don't have the unknown as the subject. So we do whatever we do to both sides. So if I want to divide or get m on its own, I need to divide m by 1.6 because 1.6 divided by 1.6 is 1. So I need to do that to both sides. So 100 divided by 1.6 will give me m. If I'm going to do a video on rearranging equations and things and different ways of doing it, you can do it algebraically or substituting the numbers in first. Some students find this much easier because they can see where the unknowns are. So now we've got mass equals 100 divided by 1.6. Mass equals 62.5. It's a mass, so it's 62.5 kilograms. Right, so now we're going to do some practice. I'd like you to think about where you are on this target. If you think you can use the formula correctly and rearrange it so you've understood everything I've just said, then you're going to do the gold level questions. If you think you can calculate the weight and you think you can do some of the harder questions, then you are in the red level. If you are a little bit confused, you think you can calculate the weight with some simple equations, you're in the blue level. If you're completely confused, so you think you're in black or white, then have a go at the blue. If you need help, send me a comment through any of the normal avenues. All right, so here are your questions. So obviously the gold questions at the top, you are going to be rearranging some of those equations. please do use Srow. I want to see Srow being used. The red questions are in the middle, and then those blue questions at the bottom. Pause the video and then come back for some answers. Write them down on a piece of paper. All right, how did you get on? What I'd like you to do is mark your answers using a green pen or anything you've got to hand, really. So the gold questions. Question 1 was 1.6 kilograms. Question 2 was 3.7 kilograms per Newton. Remember, the units are important. Question 3, 8.5 kilograms per Newton. The red questions were all about calculating weight. So the first one, question 1, 724.75 newtons. Question 2, 147,000 newtons. Sorry, 14,700 newtons. Can't read numbers today. And question 3, 36 newtons. Those of you doing the blue questions, question 1, 980 newtons. Question 2, 124 newtons. And question 3, 47 newtons. Okay, so here is a useful thing to know. Sometimes they will ask you questions like this in the exam. When a crazy person decides that it's fun to jump out of a perfectly good moving aeroplane, what will happen when they immediately fall out of the plane is they will have zero air resistance. And so they're in what's called free fall. The resultant force is just their weight, and their weight is pulling them down. And as they increase in their speed, the air resistance increases. Air resistance, remember, is just particles of the gases in the air hitting the object. So if you are a very pointy object and you make yourself streamlined, you hit less particles. So therefore, the air resistance doesn't increase as fast. If you make yourself as wide as possible, and use flappy suits so that you are maximizing the area, the surface area, then you will have more air resistance, and so that doesn't speed up as quickly. But you will accelerate. After a few seconds, the air resistance is large, but your weight never changes. So you actually start accelerating less. You're still accelerating, but the rate of acceleration is lower. So you're still speeding up. You're not speeding up as fast as you were before. About 12 seconds after jumping, your speed reaches something around the lines of 55 meters per second, depending on your surface area, and you reach what's called terminal velocity, which is where you stop accelerating. You're still falling at a constant speed, but there's no longer a resultant force. Your weight and the air resistance balance. So when this happens, you fall at a constant speed. Now, at some point, hopefully, this person is going to open their chute. If they don't open their chute, they're going to fall into the ground very hard. But when they do open their chute, what happens is the surface area increases dramatically, and so you get a much larger air resistance, and that's bigger than the weight, and so you get a resultant force upwards, and so you fall at a nice steady speed. Right, here is a common exam question. If you have the mass of a spanner on Earth of 0.2 kilograms, then its weight is 2 newtons. The spanner is taken to the moon as part of an astronaut's toolkit. Compare the mass and weight of the spanner on the moon and on the Earth. So what I'd like you to do, again, pause the video, work that out, and carry on. All right, welcome back. So here is a model answer and how many marks you would get for each part. The mass of the spanner on the moon is 0.2 kilograms. That's a mark, as the mass will remain unchanged unless your spanner changes. If you take bits off your spanner, it's going to have a different mass. But if it's the same spanner as it was on Earth, why would the mass change? It's still got the same number of spanner particles. So that's another mark. The gravitational field strength of the moon is much lower than that of the Earth. You don't even need to know what it is. Just saying that will give you a mark. So the spanner will weigh less on the moon. There you go. There is your fourth mark. So it's just that knowledge that the gravitational field strength on the moon is less, the mass is the same no matter where you are in the universe, and so the weight changes no matter where you are. Right, little plenary then, I would like you to write down 3 statements about mass and weight. 2 of them are lies. 1 of them is true. If you really want to, email these to your friends. And if they're friends that haven't seen this video, click a little link to the video as well. Help me out. If you find this video really useful, please give the like button a little boop, make it go blue, a little thumbs up. All right, everybody, please stay safe. We'll see you soon.